Hello and welcome to the first examples on Kirchhoff's law. Okay, the question says calculate the value of the current in each branch, meaning I1, I2, I3, right? Now, I1 means the current in branch AD, while I2 means the current in branch CF, then I3 means the current in branch BE. This is how it works. This I1, it is simply starting from this E. Let's say I1 is starting from E. There is no circuit element here, so we are not referencing that as a branch. Okay, for AD we have circuit elements. We have a resistor and a voltage, meaning we can say this is a branch. Then similarly, we don't have any circuit element here, so we don't reference that to as a branch. That's it. Meaning we are saying that I1, the current of I1 is for branch AD. What if I have a circuit element here? Then it means call this 2 ohm resistor. Then it means that I1 is serving for 2 branches, meaning the current in branch DE, which is 2 ohm resistor, and the current in branch AD. That's the first thing you need to understand. The same ideas applies. The current I2 is serving as the current for branch CF, since there is no circuit element in branch BC, neither branch EF. That's the first thing you need to understand. And for branch BE, I3 is serving for the current in branch BE. Okay? As we know, I've explained in my introductory video, we have what we call loop and what we call mesh. If you haven't watched that video, do so to watch the video. Okay? This is loop 1 and this is loop 2. Now, when it comes to Kirchhoff's law, we have what we call assumed direction. And the assumed direction is we have the clockwise direction and we have the anti-clockwise direction. Now, this is how it works. When you are given a question, it's either you go both clockwise direction and clockwise direction, or you go clockwise direction, anti-clockwise direction. You know, this is just 2 loops. We are having 2 loops here. What if we have more than 2 loops? Let's say 3 loops or 4 loops. It is still the same idea of 2 loops that you are going to implement. So I want you to give your maximum attention to this. Okay, now take note, when it comes to direction, let me split branch AB, branch BE, and branch BC. Let me bring it out. Let's bring branch. This is A, B, C, and E. From my diagram, I'm having something of this nature. This is I1, this is I2, and this is I3. What I can deduce from here, from KCL, Kirchhoff current law, says that the algebraic sum of a current entering a junction is equal to the algebraic sum of currents leaving that junction. Now, observe, I1 is entering junction B, while I2 and I3, they are leaving junction B. Meaning, from here, we have a mathematical expression saying that I1 is equals to I2 plus I3. This is your first equation. Call this case 1. This is case 1. Case 2. Case 2. What if I have my junction in this manner? We have something of this. This is I1, this is I2, and this is I3. Now, observe, applying KCL to case 2, it means I1 is entering junction B, I2 is entering junction B, and I3 is leaving junction B. A mathematical equation for that from KCL, summation of currents entering a junction is equals to the currents leaving that junction, meaning that I1 plus I2 is equals to I3, right? This is your first task when it comes to Kirchhoff's law. But there's something that brought up this that I want to say. Now, for case 1, you know, this is loop 1, this is loop 2. That's what I just splitted here. This is loop 1 and this is loop 2. For case 1, what it means is that for both loops, you've assumed the direction you assumed is clockwise direction for loop 1 and clockwise direction for loop 2. That's the meaning. Meaning, for loop 1, you've assumed this direction. you've assumed this direction. Meaning, whenever you have this equation, your assumed direction for the two loops are both anti-clockwise direction, right? What if you have this equation from case 2? It means one is clockwise direction while the other is anti-clockwise direction. Okay, this is it here. So for this example, both loops will be considered clockwise direction. My next example, both loops will be considered clockwise and anti-clockwise direction. All right, let's get it done. Meaning, we are saying that loop 1 is clockwise direction, while loop 2 is also clockwise direction. Okay, this is loop 2. And one thing I want us to know as well, when it comes to clockwise direction and anti-clockwise direction, you know, your batteries has its polarity. When I say polarity, I mean the positive terminal and negative terminal. Let's see this. The positive terminal is the longest side, while the short side is the negative terminal. What about your resistor? The polarity of the resistor depends on the direction of the resistor. Okay, let's consider this resistor, and you have your direction, and you have your current going in this direction. What will be the polarity of this resistor? This will be positive, and this will be negative as well. Call this 1. For 2, let's say you have your resistor in this manner. And your current is going in this direction. What will be the polarity of this resistor? This will be positive and this will be negative. So case 1 and case 2 of assigning polarity to resistor, that's what we'll be using in its clockwise or anti-clockwise direction. Let's see this. When our assumed direction is clockwise, let's see how it looks like, how the polarity of our resistor looks like in a closed loop. Similarly, when our direction is anti-clockwise, let's see how our polarity looks like for resistor in a loop. Okay, let's say I have direction, this is clockwise direction, and this is anti-clockwise direction. And let's say we have our resistor, we have this circuit, a closed circuit. This is A, B, C, and D. Now, this is a loop, right? A, B, C, D. Let's say the assumed current direction to this circuit is a clockwise direction. We are applying clockwise. We are applying clockwise direction to this resistor. Then what will be the polarity of this resistor in branch AB, branch BC, branch CD, and branch DA? This is it. Since I'm going in a clockwise direction, meaning I'm starting at A. Clockwise, I'm starting at A. So I'm going in this manner from A to B, from B to C, going in this manner from C to D, then from D to A. Right? Now, recall, when it comes to assigning polarity to resistor, we said that the polarity of your resistor depends on the direction of it depends on the current direction. Now, for A to B, my current is going in this manner, then the polarity of this resistor becomes positive, negative. For branch BC, I'm going in this manner, then the polarity becomes positive, negative. From C to D, I'm going in this manner, then the polarity becomes positive, negative. Similarly, for D to A, I'm going in this manner. The direction of my current is in this manner. This is positive, negative. This is when you assign a clockwise direction to your loop. This is what you have, assigning polarities to your resistor. Anti-clockwise, this is case 1. For anti-clockwise, same idea, right? Let's say this is my resistor, this is my loop or my circuit per se. This is A, B, C, D. The difference is for clockwise direction, you started from A, right? You started from A, then back to A. But for anti-clockwise direction, you will be starting at B, then back to B. Bear this in mind. This is very, very important. For A, when it comes to clockwise direction, you are starting at A and you are going back to A. For anti-clockwise direction, you are starting at B and you are going back to B. Meaning, from B to A, the nature of the current becomes this, right? B to A to D, D to C, D to C, you have this, then C to B, you have this. Then as usual, the polarity of your resistor depends on the direction of the current. Meaning for branch BA, this becomes your positive, negative. For branch AD, this becomes your positive, negative. For branch DC, this becomes your positive, negative. Then for branch CB, this becomes your positive, negative. So that's it. This is very confusing, but with this, I believe this should help you in understanding how you can assign polarity to your resistor. Take note of this. The difference is that for clockwise direction, you are starting at A, then back to A. For anti-clockwise direction, you are starting at B, then back to B. So that's what we'll be applying here. Solution. Loop 1, I'm going in a clockwise direction. Loop 1, I'm going in a clockwise direction. Loop 2, I'm going in a clockwise direction. Let's apply this idea here, this man here. Let's apply it here to this loop 1. From A to B, we have the direction of our current in this manner, right? We have the direction of the current in this manner. From B to C here is our B to E here. We have the direction like this. That's BE. The current is coming like this. Check. Your polarity for your resistor, you are having positive, negative. Similarly, for this resistor, for this 2 ohm resistor, this becomes your positive, negative. You are done with BC. Moving on, CD, which is my ED here. I don't have any resistor here. I'm moving on, right? Then back to DA. Your current is going in this direction. This becomes your positive, negative. That's the same idea you are going to implement here. There will be the positive and negative terminal of this 0.5 ohm resistor. Yes, you are correct. This will be the positive and this will be the negative. This is very crucial when it comes to direction. You need to understand these basics. Okay? Alright, loop 2. Still ask yourself, loop 2, I'm still going in a clockwise direction. Clockwise direction. Meaning I'm starting from B to C, C to F to E, E to B. I'm going like this. There's no resistor. I don't have any business with BC then. From C to F, this man here, I'm having a resistor of 5 ohms. The polarity becomes positive, negative. That's it. We have positive, negative. Right? For FE, I don't have any resistor here. So I'm less concerned with that. Okay? Moving on, EB, which is your DA here. The polarity of the resistor involved becomes positive, negative. Similarly, here, what do I have? I have positive and negative. So that's it. Your first assignment or your first task is to assign polarities to the resistor involved in the circuit depending on the assumed direction. Okay? Having done that, the next thing, note, when you are going from positive terminal to negative terminal, there's a voltage gain. When you are going from positive to negative, there's a voltage gain. From negative to positive, there's a voltage drop. Starting from loop 1, meaning mesh A, B, E, D, A. For AB, no circuit elements. Take note, this 2 ohm resistor is between loop 1 and loop 2. That's why the resistor is having its polarity twice, meaning positive, negative for loop 1 and positive, negative in this manner for loop 2. Okay? Now, considering loop 1, meaning mesh AB, E, D, A. A to B, no circuit elements. Move on. B to E, I'm having two circuit elements. I'm having a battery and I'm having a resistor, right? Now, this battery, it is moving from a negative terminal to a positive terminal to positive. And if you are going from negative to positive, there is a voltage drop. So therefore, 12 voltage becomes minus 12. Why? Because it is moving from negative to positive. Hence, voltage drop. Then for this 2 ohm resistor, 2 ohm resistor is having its polarity both in loop 1 and in loop 2. Consider loop 1. Considering the first loop, which is loop 1, the current in loop 1 is I1, and the polarity in this case is positive negative. Positive to negative, there is a voltage gain. Okay? Considering loop 1, positive to negative, that's plus 2I1. Why is it plus? Positive to negative, voltage gain. The value of the resistor 2. Then what the current of loop 1? I1. You are done with that. For the other side, which is loop 2. For loop 2, the current in loop 2 is I2, right? The terminal, it is moving from negative to positive. From negative to positive. And if you are going from negative to positive, there is a voltage drop. That is negative 2I2. Where is this negative coming from? Negative to positive, voltage drop. The value of the resistor, 2. Loop 2, what's the current in loop 2? I2. That's it. We are done with this resistor. Then branch ED, no circuit element. Move on. DA, we are having two circuit elements. The first one is this resistor, right? This resistor, it is moving from positive to negative. And if you are going from positive to negative, there is a voltage gain. Positive 0.5 I1. Why is it I1? 0.5 is present in loop 1, and the current in loop 1 is I1. That's it there, right? Then you are having a battery. You are having this 4 volts. This 4 volts is moving from negative to positive. Negative to positive, there is a voltage drop. Hence, you have minus 4 equals 0. What you just did here, you applied KVL. After writing loop 1 mesh A, B, E, D, A, say the condition applying KVL. By definition, KVL states that the algebraic sum of voltage in a closed loop is equals to 0. That's what we've done here. 2I1 plus 0.5 I1 minus 2I2 minus 12 minus 4 equals 0. From here, we have 2.5 I1 minus 2I2 equals to, this is minus 16. This is minus 16. Of course, if minus 16 is going to the other side, you have positive 16. Call this equation 1. Moving on to the next loop. Loop 2. For loop 2, mesh BCFEB. For loop 2, mesh BCFBE. Applying KVL, that states that the algebraic sum of current in a closed loop is equals to 0. Same idea. From B to C, no circuit element, right? C to F, I'm having 5 ohm resistor. How do you convert your resistor to your voltage? First thing first, in what's the polarity of this resistor? It is moving from positive to negative, meaning there is a voltage gain. Positive 5. What is the current of this 5 ohm resistor? This 5 ohm resistor is present in loop 2. And what is the current of loop 2? I2, meaning positive 5 I2. Right? For branch FE, no circuit element. For branch EB, you are having this resistor moving from positive to negative. From positive to negative, there is a voltage gain. That's positive 2 I2. 2 ohm resistor is in between current. It is in between loop 2 and loop 1. For loop 2, the current in loop 2 is I2, and it is going from positive to negative, meaning voltage gain. That's the positive. The value 2, the current in loop 2 is denoted as I2. That's what we have here. Okay, then consider this resistor in loop 1. It is moving from negative to positive. When you are moving from negative to positive, it means there is a voltage drop, that is negative 2 present in loop 1, right? What the current in loop 1? I1. Yes, you have your I1. Then you are done with 2 ohm resistor. Moving on, you have this battery, positive, negative. You are going from positive to negative. There is a voltage gain, meaning positive 12. Then I said earlier, you are starting from A and you are going back to A. That's what we applied here. We started from B and then we went back towards B. Then we are done with KVL. Then equate that to 0. Then from here, collect like term. Negative 2I1 plus 7I2 is equals to negative 12. Call this equation 2. Solving equation 1 and 2. From equation 1, we have 2.5 I1 minus 2I2 equals to 16, and equation 2 minus 2I1 plus 7I1 equals to minus 12. Now, equation 1 and equation 2, you can use simultaneous equation and you can also use the Cramer's rule, meaning matrix. I'll be using matrices to solve this, just to see how we can solve a simultaneous equation using matrix. Alright, your first task when it comes to solving equation 1 and equation 2 using matrix, what you just need to do, bring out your rows and columns. This is 2.5 minus 2 minus 2, 7, and you have 16 minus 12. Right? Now, calculate the value of your determinant, your original determinant. Calculate the value of delta 1, that means the determinant 1. Calculate the value of the original determinant. Calculate delta 1 and delta 2. Meaning the original determinant, the first determinant, and the second determinant. And from here, so therefore, I1 is equals to the ratio of delta 1 to the original determinant, and I2 is equals to the ratio of determinant 2 to the original determinant. So therefore, let's solve for the original determinant, the delta 1 and delta 2. Okay, for the delta itself, this is 2.5 minus 2 minus 2, 7. Determinant, what you just need to do, 2.5 times 7 minus 2 times minus 2. 2.5 times 7, that gives us 17.5 minus 2 times minus 2. That's positive 4, right? Then this becomes 13.5. So therefore, your delta is equals to 13.5. Okay, let's solve for delta 1. When it comes to delta 1, what you just need to do, 16 and minus 12, represent it here, right? Meaning you have 16 minus 12, then this remain constant, minus 2 and 7. Okay, now what will be delta 2? As the name implies, delta 1, you are substituting 16 and minus 2 to this column. For delta 2, you are going to substitute 16 and minus 2 to this column. That's it. Then for delta 3, if there is delta 3, you are going to substitute 16 and minus 12 to the third column. That's the matrix class. We do more of that in matrix class. But for delta 2, then for your delta 2, you have 2.5 and minus 2. Then these columns becomes 16 and minus 12. Okay, let's find the determinant. For the determinant of delta 1, that's 16 times 7 minus 2 times minus 12. 112 minus 2 times minus 12, that's positive 24, and this is equals to 88, meaning delta 1 is equals to 88. Let's find the determinant of delta 2. That's 2.5 times minus 12 minus 2 times 16, and this gives me minus 30 minus 2 times 16, that's minus 32, right? Meaning minus 30 plus 32, and minus 30 plus 32 simply means positive 2. So therefore delta 2 is equals to 2. Now if you obtain the value of delta to be 13.5, we've obtained delta 1 to be 88 and delta 2 to be 2. Let's get the value of I1 and the value of I2. I1 is equals to your delta 1, that's 88. 88 divided by your delta, that's 13.5, which is equals to 6.518 amperes. That's I1. Then I2 is equals to 2 divided by 13.5, and this gives me 0.148 ampere, right? You've solved for I1, I2. What about IP? IP at junction B, the value of your I3 from at junction B, applying KCL, you have I1 is equals to I2 plus I3. Make I3 the subject of the formula, meaning I3 is equals to I1 minus I2. Substituting the value of I1 and I2. So therefore I3 is equals to 6.51 minus 0.148, and that's equals to 6.37 ampere. So therefore the value of I1, I2 and I3 are 6.518 ampere, 0.148 ampere and 6.37 ampere respectively. You will notice that all value of current are positive. What this means is that the assumed direction of current was correct. What we assume to be the current direction is correct, meaning the clockwise direction assumed for loop 1 and the clockwise direction assumed for loop 2. Both directions are correct. In a case whereby the value of I2 is negative, it means, and we've assumed clockwise, it means the actual direction is anti-clockwise and not clockwise. Okay, we see more of that in another video. In the subsequent video, the direction I'll be using for the two loops, one will be clockwise direction and the other will be anti-clockwise direction, just to see how we can use both clockwise and clockwise direction, clockwise and anti-clockwise direction, anti-clockwise and anti-clockwise direction. Whichever direction you are going with, at the end you are going to get the same thing. It just depends on you understanding the principle and implement. See you in the next video. Check the description below to access the next video. See you in class. Don't forget to like, share and subscribe if you are new to the channel. Also comment to the channel to share your thoughts. All right.